Hello everyone, my name is Aritra. This work is done in collaboration with Stefan Gumhold, Carsten Rother, and Eric Brachmann. Today I'll be talking about reinforced feature points. In recent years, neural networks are used to implement detection and description of features in images. State-of-the-art networks like SuperPoint are able to perform as good, if not better, feature detection and description as the well-used handcrafted designs like the seminal SIFT algorithm. SuperPoint produces better result than SIFT on a low-level matching task like H-patches, which deals with finding key points and matches between image pairs. However, when trying to solve a high-level vision task like relative pose between two camera positions, SuperPoint performs much worse than SIFT, despite finding increased number of key points in the image pairs than SIFT does. Most learned detectors, which learn to produce key points and descriptors, behave in a similar fashion. The reason lies in the training methodology of such detectors. Let us view the training pipeline of one such method, the SuperPoint. A base detector is pre-trained on synthetic data, then it is used along with homographic adaptation to find pseudo-ground truths, and then CNN is trained with key point and descriptor losses. But to obtain a pose estimate between camera positions, we need to apply a robust estimator like RANSAC with a 5-point solver to find the essential matrix, decomposing which yields the relative transformation, all of which is not taken into consideration for training the SuperPoint network. In our work, we embed the feature detection and description in a computer vision pipeline for training. But key point selection and matching are discrete non-differentiable operations, so we cannot directly backpropagate gradients from the estimated transformation to train the network. Instead, we use a training formulation inspired by reinforcement learning. We use SuperPoint architecture to generate key point heat maps from input images, randomly sample key points from this heat map, and then obtain descriptors from the selected key points. We implement probabilistic matching by firstly doing an exhaustive matching, secondly calculating a distribution over all matches, and then sampling a subset of matches which is passed to the black box to get the relative pose. The training objective aims at reducing the expected task loss. The steps that are undertaken include sampling key points, sampling matches, and then finally calculating the pose loss. For gradient calculation, only the derivatives of log probabilities of key point selection and feature matching are required. Note that processing pipeline after feature matching produces the loss value, which need not be differentiable for training the network. Now we visualize the difference in key point heat map predicted by SuperPoint before and after our end-to-end training. Key points which appear blue were discarded, whereas key points with a gradient from blue to red were moved, all in accordance with minimizing the pose loss. Such phenomena are seen a lot in case of repetitive patterns. To study the effect of reinforcing feature description, we take image pairs, find key points using initial SuperPoint, perform exhaustive matching. We visualize the difference in matching probabilities before and after the training. Probabilities of red matches are increased by reducing their descriptor distances. Now we take a look at some results. In case of low-level matching tasks like H-patches, our network achieves state-of-the-art, improving over SuperPoint. In case of high-level tasks like relative pose estimation, we improve over SuperPoint but remain below SIFT when we use RANSAC. But when we use a sophisticated estimator like NG-RANSAC, we reach state-of-the-art. We show results of estimating the relative pose between these two images. We achieve much more inlier matches with respect to ground truth essential matrix, green being inliers and red the outliers. Our pipeline is flexible to accommodate any kind of feature detector network in combination with any robust estimator and can be trained for computer vision tasks as required.